quadratic forms. So first of all, tell me whether my voice is clear or not. Just raise your hand if my voice is clear. Okay, it's all right. So now I'm going to upload the PowerPoint slides. Wait a minute. If A is related to D uh, by a similarity transformation such that D is equal to M inverse AM. So in my face-to-face class, I wrote that A inverse A we write D inverse AM. So there is no notation. Don't confuse with the notation. So the theme is the summary is same. So here it is written as D is equal to M inverse AM. Then A is reduced to the diagonal matrix D through the model matrix M. D is called the spectral matrix of A. So reduction of a matrix to diagonal form. A square matrix A of order n has a linearity in independent eigenvectors. Then the matrix B can be found such that B inverse AB is a diagonal matrix. So the matrix B which diagonalized A is called a model matrix of A, and it is obtained by grouping the eigenvectors of A into the square matrix. So let us see how we use that. So here they are showing that how we can write that. So these all things we learned in previous weeks. So let's take an example. After that, we will come to our main topic, today's topic, that is orthogonal reduction. So this example for the orthogonality. So it says that there is a matrix of 3 by 3 matrix to diagonal form by similarity transformation. Hence, find A3. So as I told you, there are 3 steps are there to, if you want to diagonalize a matrix, there are 3 steps. In step number, there are 3 steps are there. In step number 1, find the eigenvalue. Find the eigenvalue. In step number 2, find the eigenvector. And step number 3, find the P, capital P, such that P is equal to P1, P2, P3, P4, and so on. And such that you can write that will be is equal to P inverse AP. That is called that you have to write in this form. That is called the diagonalization. So in these 3 steps, we will solve this problem. So our step number 1, we will start our step number 1. Find the eigenvalue. This is step number 1. Find the eigenvalue. So we know how to find the eigenvalue. First of all, we will write the characteristic equation. So the characteristic equation is lambda I minus A. So either you can write lambda I minus A, or you can write A minus lambda I. Lambda I minus A will be is equal to 0, or you can write A minus lambda I. A minus lambda I will be is equal to 0. So will be is equal to 0. Both are the same thing. So this is called the characteristic equation. So we will write here from this equation, if there is A, so we will write A minus lambda I. But there is 1 minus lambda, and here it is 2. So we write 2 minus lambda, 3 minus lambda, and rest of the places like minus 1 here, 2 here, and minus 1 here. So rest of the places like same. So in my face-to-face class, we use lambda I minus A always we use. So but here in PowerPoint slides, they are using A minus lambda I. So don't be confused. Both are the same results. There is no any change in this. So it is a 3 by 3 matrix. So when you open this determinant, you will get there are the three roots of lambda. Lambda is equal to 1, lambda is equal to 2, and lambda is equal to 3. So these three roots are called the eigenvalues. So all of you know how we can calculate these eigenvalues. So tell me how many eigenvectors are there if we have three eigenvalues. So how many eigenvectors are there in this? There are two, yes, not 63, it is 3, yes, you are right. There are three eigenvectors are there, yes. First eigenvector corresponding to lambda is equal to 1, second eigenvector corresponding to lambda is equal to 2, third eigenvector corresponding to lambda is equal to 3. So these are three eigenvectors are there. So one by one we will found the eigenvectors. So first of all, eigenvector corresponding to lambda is equal to 1. So when we found the eigenvector corresponding to lambda is equal to 1, we will found the eigenvector will be 1, 0, 0. So similarly, second eigenvector we will found corresponding to lambda is equal to 2. We will found that the eigenvector will be is equal to 1 minus 1, 0. And the third eigenvector we will found corresponding to lambda is equal to 3. We will found that the eigenvector will be is equal to 3 minus 2, 2. So you will see these calculations at your home, how we can calculate these calculations, you will get. So these three eigenvectors we will found, that is P1, P2, P3. So now we combine all these three eigenvectors. So in A1 matrix, so we will comprise these eigenvectors in one matrix. That is, this is P1, and this is P2, and this is P3. So these eigenvectors we will write in one matrix. So now our aim is find P inverse AP. P inverse AP. AP. This is P. Here they use M, but in my physical class I use P. So this is P. So now we have to write these things. P inverse AP. So we will find P, and now our aim is to find the P inverse. So we know the formula of to find the inverse. There are two ways to find the inverse. The first way is by the row reduction methods. We can find the inverse. The second formula is find the AM in find the M inverse is equal to adjoint of M upon determinant of. This is the second formula. So we have to find the P inverse using this formula. We will find this is P inverse. Using this formula, we will find. So first of all, find the determinant of P. So determinant of P will be is equal to 2. Is if you find the determinant, solve them, you will find minus 2. And adjoint of M. So adjoint of M, you will find when you calculate the adjoint of M, you will get this minus 2, 2, 0, 1. So I told you this adjoint, and in a week 2 or week 1 or week 2 classes, I told you how to find the adjoint, of the matrix. So this way you will find the adjoint, and in this way you will find the inverse of P. So this is the inverse of P, adjoint M upon determinant of M. So this is the inverse of P. Now put in this formula P inverse AP. So multiply these three matrices, we will get. So multiply, this is P inverse, and this is A, and this is P. So multiply these three matrices, we will get this matrix. This is a diagonal matrix. That is, this is a diagonal matrix. So in this way, we can find the diagonalization of the matrix. So this is these things we discussed in previous weeks. So now we are going to proceed. If we have a orthogonal transformation of a symmetric matrix to diagonal form. So if we have an orthogonal, so here we say that the process is same. There is nothing changed. Only in place of inverse, we will put the transpose of this. So before discussing that, there is some definition. Here you say that a square matrix with the real element is said to be orthogonal if A into A transpose is equal to I. A into A transpose, or A transpose into A is equal to I. A into A inverse is equal to I. A into A inverse as follows. A is orthogonal. So there are some definitions are there. If A is a real symmetric matrix, then eigenvectors of A will not be only linearly independent but also pairwise orthogonal. The similarity transformation, so these are some definitions are there. You will read these definitions. So and now diagonalize the matrix by means of the orthogonal transformation. Now this is the second example. We will solve it by the orthogonal transformation. So as I told you, here is again there are the three steps are there. Step number 1 is step number 2 and step number 3. The same steps are there. First step, find the eigenvalue, and in the second step find the eigenvector, and in the third step find the p. P will be is equal to p1, p2, p3, and so on. And after that, that is equal to p transpose AP. We will write the orthogonal transformation will be p transpose AP. So step number 1 is same, step number 2 is same, step number 3 slightly difference is that in place of inverse we will use the transpose only. So this is the only difference between orthogonal transformation and simply diagonalize the matrix. So we have this matrix is so first of all, write the characteristic equation number 1. Our step number 1, find the eigenvalue. To find the eigenvalue, we have to write determinant of a minus lambda I, or you can write lambda I minus a minus lambda I will be is equal to 0. In this way we can find the eigenvalue. This is the characteristic equation. We will find the eigenvalue of this characteristic equation. These are the three eigenvalues of this characteristic equation. So these are called these are three eigenvalues. So these are called the eigenvalues, and the eigenvectors corresponding to these eigenvalues. How many eigenvectors? So we know that there are three eigenvalues. So there must be three eigenvectors are there. So eigenvectors, let us see the eigenvector corresponding to lambda is equal to -2, eigenvector corresponding to lambda is equal to 6, eigenvector corresponding to lambda is equal to 6. So we will find the eigenvector corresponding to these. So one by one we will find eigenvector corresponding to lambda is equal to -2. We will find 1, 0, -1. Similarly, we will find the eigenvector corresponding to lambda is equal to 6. So we will find the eigenvector will be is equal to 0, 0. And the third one will be eigenvector corresponding to lambda is equal to this we will find 0, 1, 0. So we will combine all these eigenvectors. This is the matrix will be is equal to this is the P. When we combine all these things, we will get 1, 0, -1, 1, 0, 1, 0, 1, 0. So now normalize the model matrix. So we will get this. So this is P now, and this is P. So we will take a transpose. So this is first row. When we take the transpose, it will become the first column. Similarly, this is the second row, and when we take the transpose, it will become the second column. This is the third row. When we take the transpose, it will be equal to the third column. So, and this is the A, and this is the A beats P. So we will write whatever the P it is, we will write like this. So P transpose AP. This is P transpose A and P. So just we will multiply, we will get this matrix that is a diagonalized, which requires a diagonal matrix. So this is a, uh little bit lengthy long methods. So these are not too much important. So there is no need to concentrate on this topic hardly. Just see this, how we can solve it, and there is no need to focus on this topic. So because of it's very lengthy. So now let's move to next topic. The next topic is quadratic forms. So if a homogeneous polynomial of second degree in any number of variables is called a quadratic form, for example, ax square plus 2hxy plus by square. Similarly, if we have ax square plus by square plus cz square plus 2hxy plus 2gx 2fz, this is a quadratic form. Similarly, another type of equation, this is our quadratic form in 2, 3 and 4 variables. So this is in 2 variables, this is in 3 variables, and this was in 4 variables are there. So now the question is how we can write these type of quadratic forms in the form of the matrix. So let us see. If we have this 3 variables are there and we have to write this quadratic form, so first of all we will write the diagonal elements. So here it is x square, coefficient of y square, coefficient of z square. So I write in the diagonal element a, b and c here. Whatever the means, whatever the square terms, we will write in the diagonal forms. After that we have a h, yani 2hxy. So we will write h into h here and h here on the left and on the right. And next one will be 2gx. So g will be here, we will write here and here. And similarly 2fxy. So we write f here and f here. In this way we will write the whole matrix. Similarly, if we have like if we have again, if we will see this, if we have like this like any 4 variables, ax square plus by square plus cz square plus dw square, this is a square. If we have 4 variables, so how we can write? First of all we will write the first of all we will write the main column. This is a, b and c, d. So the coefficient of x square, the coefficient of y square, the coefficient of z square, and the coefficient of w square. So we will write a, b, c, d. And after that I will write h here, and after that I will write f here, and here it is L here, M here, and M here, and N here, and here. So in this way we will write the matrix. So let's see nature of the quadratic form. So nature of the quadratic form, there are 3 types of natures are there. First nature is called the positive definite, and the second nature is positive definite means if all the eigenvalues are positive, then we say that it is a positive definite. Similarly, if all the eigenvalues are negative, then we say that it is a negative definite. If positive some semi-definite, if all the eigenvalues are and at least one eigenvalue is 0. Negative semi-definite, if indefinite, if some eigenvalues are positive and some eigenvalues are negative. That is called the indefinite. So these are the definitions. We will discuss these definitions. We can understand this definition with the help of example. So there are this is a question, and there are two examples are there. The example number one is find the nature of the following quadratic forms. So there are two questions are there, question number one and question number two. So find the nature of the following quadratic form. Nature means just you have to tell us whether it is a positive definite, it is a negative definite, or it is indefinite. So to find the eigenvalue, because of for the positive definite or negative definite, we have to find the eigenvalue. Because the definition of the definite is if all the eigenvalues are positive, then it is definite. So let us see. This matrix is given, and we have to find the eigenvalue first. So first of all, we will write the characteristic equation. When you write the characteristic equation, you will get whatever you will get, and you will get the three roots are there. That is -2, 3, and 6. So tell me which clause will be fulfilled. That is, all the eigenvalues are positive, or all the eigenvalues are negative, or some eigenvalues are positive and some eigenvalues are negative. So this is the third part is appear here. So this is called the given quadratic form is indefinite. So if you have any question, then you can ask me, or you just see the second part. I will give you 1 minute. So we will see this, that these two eigenvalues are being positive and one being negative. The given quadratic form is indefinite because of from the definition we see in previous slides. From the definition we will see this. If some eigenvalues are, if definition number 5, If we see this, if some eigenvalues are positive and some eigenvalues are negative, then we say that it is indefinite. So now let's see the question number second. It says that the matrix is the question number 2 here. So this is the matrix, this is the quadratic form is given. We have to write the matrix. So to write the matrix, first of all, we have to write the diagonal elements. So what are the diagonal elements? First of all, we will write 3. So 3 here, and after that we will write 5. So 5 here. After that we will write 3 here, and after that I will write, this is minus 2. This is minus 2. So we will write minus 1 and minus 1 here. And here this is 2. So I will write 1 and 1. Here it is minus 2. I will write 1 and minus 1 and minus 1. So in this way we will write the matrix. Let us see whether this is the same matrix or not. So 3 minus 1, 1. So we will see this is the same matrix. So hopefully understand how we can write the matrix from the quadratic form. So in this way we will write the matrix. So now from this matrix, write the eigenvalues. So the eigenvalues of A are 2, 3, 6. So these all the eigenvalues are positive. It means all these eigenvalues are being positive. The given quadratic form is positive definite. So in this way we will write from the equation to the matrix form. We can write in this way. So now up to here. Now again there are some questions of the diagonalization. So we will read these things already. There are some more questions of the diagonalizable matrix. So you can see these corresponding to the 3 eigenvectors are there. A matrix is not diagonalizable. Show that the following matrix is not diagonalizable. So let us see, it is a 2 by 2 matrix. Let us see whether it is diagonalizable or not. So as I told you, to check the diagonalizability. So there are 3 steps. For step number 1, find the eigenvalue. Step number 2, find the eigenvector. Step number 3, find the p. So let us see. First of all, is step number 1, find the eigenvalue. So the characteristic equation is lambda I minus a will be equal to 0. So lambda I minus a we will write in this way. So lambda minus 1 and minus 2, 0, lambda minus 1. Multiply this lambda minus 1 into lambda minus 1 whole square, and 0 into minus 2 will be 0. So lambda minus 1 whole square will be equal to 0. So lambda is equal to 1. Now find the eigenvector corresponding to this. So when you find the eigenvector, that is only one eigenvector, that is P1 is equal to 1, 0. So that is why, because of there is only one eigenvector, that is why it is a linearly independent eigenvector. So it is not a diagonalizable. Because if we have a second one eigenvector, then we say that it is a diagonalizable, but it has only one eigenvector. That is why it is not a diagonalizable. So these are the same steps are there. Some more questions are there from the diagonalizing matrix. So here again there is a 3 by 3 matrix, and find the matrix P such that P inverse P is diagonal. So the same step is right. The step number 1 is find the eigenvalue. That is to find the eigenvalue, we have to write the characteristic equation. That is lambda minus a. This will be is equal to in this way. Hence the eigenvalue will be like this. Similarly, find the eigenvector corresponding to lambda is equal to 2, corresponding to lambda is equal to minus 2, corresponding to lambda is equal to 3. So there are 3 eigenvectors are there. So corresponding to lambda is equal to 2, the eigenvector will be in this way: p is equal to -1, 0, 1. Similarly, corresponding to lambda is equal to -2, the eigenvector will be 1, -1, 4. And corresponding to lambda is equal to the third one, that is lambda is equal to 3, the eigenvector will be equal to -1, 1. And adding all these eigenvectors, we will write p1, p2, p3. So we can write in one bracket all the eigenvectors in one bracket, that is -1, 0, 1, 1, -1, 4, and -1, 1, 1. So this now find the P inverse AP. So to find the P inverse AP, that is, we can write the P inverse AP will be is equal to 2 minus 2, 3. That is a diagonalizable. So there are some more examples are there, you will see. So now the next topic is matrices, related to matrices. So there are several types of matrices are there, that is symmetric matrix and orthogonal diagonalization. So the definition of the symmetric matrix is: a square matrix A is symmetric if it is equal to its transpose. Means A is equal to A transpose. So then we say that it is a diagonalizable. It is a symmetric matrix like that. So this is the question: symmetric matrix and non-symmetric matrix. So tell me whether this is a symmetric matrix or not. So we say that yes, it is a symmetric matrix. Why? Because of here 1 and here 1, here -2 and here -2, here 0 and here 0. So it means that it is a symmetric matrix because of from the diagram on the left hand side and the right hand side, all the elements are same. That is why we say that it is a symmetric matrix. What about the second B part? If you see in the B part, where it's a diagonal is will be 4 and 3, 4 and 1 in the diagonal, and rest of the places are 3 and 3. So both are same. So we can say that it is a symmetric matrix. Now similarly, the C part, in the C part you will see this is the diagonal, and when you see the left hand side and the right hand side is not equal, so you say that it is non-symmetric matrix or it is not symmetric. So there are some properties of the matrix. So the properties are: if A is n cross n symmetric matrix, then the following properties are true. A is diagonalizable. All eigenvalues of A are real. If lambda is the eigenvalue with A multiplicity k, then lambda has k linearly independent eigenvectors. That is, the eigenspaces of lambda has dimension k. A square matrix P is orthogonal if it is invertible, and P inverse is equal to P transpose. Or you can say that P inverse into P transpose will be is equal to P transpose. Or you can, if you take on the left hand side, on the right hand side, so what it will be: P transpose into P will be is equal to I. So if you prove like this, P into P transpose, that will be equal to I, then you say that it is a orthogonal. So there are two sections. This is one part and this is second part. So whichever you want better, you can solve them. So orthogonal matrix. So number one question is, P is equal to 0, 1, -1, 0 is orthogonal because of P inverse is equal to P transpose. So it means that it is orthogonal. Similarly, the B part is, there is a 1, 2, 3, 4, 4 by 3 matrix is there. So we can write P is equal to this is orthogonal because P is equal to P transpose of this. Properties of the diagonal matrix. So the property of the diagonal matrix is we can write P into P transpose, that will be is equal to 1. This is the first property. Properties of the symmetric matrix. It says that eigenvalue of a symmetric matrix show that any two eigenvectors of A corresponding to distinct eigenvalues are orthogonal. So we can prove this. Fundamental theorem of the symmetric matrix or orthogonal diagonalization of the symmetric matrix. Find all that eigenvalues of A, determine the multiplicity of each. For each eigenvalue of multiplicity, say, choose a unit eigenvector. For each eigenvalues of multiplicity, this is equal to. So there are some definitions you will read. Determine whether the matrix is orthogonally diagonalizable or not. So we first of all we'll say that whether it is symmetric or not. We will like this is our main diagonal, and what about the left hand side and the right hand side? So this is the left hand side, this is the right hand side, left hand side, right hand side, left hand side, right hand side, both are equal. So it means that it is a symmetric. Similarly, we can find the orthogonally diagonalizable. So we say that yes, it is orthogonally. Now, secondly, A2 will be symmetric or not. So just draw the main diagonal and just see the left hand side and the right hand side, it is equal or not. We see that 2 will be equal to 2 and minus 1 will be is equal to 1. So no, this is false because of minus 1 is not equal to 1. And similarly, the third A3 will be equal to, this is not asymmetric because of it is not a square matrix. Similarly, this one will be symmetric because of left hand side is equal to right hand side. So in this way we can show that. So there are some more definitions are there. Skew symmetric, and orthogonal matrix. A real square matrix A is called asymmetric if its transpose leaves it's unchanged. A transpose is equal to A. Skew symmetric if transpose gives the negative of A. Any real square matrix A may be written as the sum of the symmetric matrix R by symmetric matrix S, where R is equal to this 1 by 2 A into A transpose. Hermitian, skew Hermitian, and unitary matrix. A square matrix A is called a Hermitian if A bar transpose is equal to A. That is, A k j bar is equal to A j k. And skew Hermitian, in skew Hermitian, the same example, only put the minus sign. And what is a unitary matrix? Unitary matrix if A bar transpose is equal to A inverse, that is called the unitary matrix. Theorem: the eigenvalue of Hermitian matrix and thus of a symmetric matrix are real. So from this example, I give you the one example in my physics class where we see that the eigenvalue of the Hermitian matrix are real. So that question is related from this theorem. So the B theorem is the eigenvalue of a skew Hermitian matrix and thus of a skew symmetric matrix are pure imaginary. Similarly, next one is the eigenvalues of a unitary matrix and thus of an orthogonal matrix have absolute value 1. So there are some definitions are there. You will memorize them. Determinant of a unitary matrix. Let A be a unitary matrix, then its determinant has absolute value, that is, determinant of A will be is equal to 1. So in this way, we can, you will see some more examples on the matrix and understand. So it is the end of today's lecture. If you have any question, then you can ask me. If you have any question related to the matrix, related to the quadratic form, then you can ask me. Hopefully you understand how we can write the matrix from the quadratic form. Maybe it is clear for you. If you are not, then you can see the PowerPoint slides. These slides are uploaded on the Blackboard. And the second thing is, I upload the assignment number 3 today. Please check your Blackboard and download the assignment from that Blackboard and try to solve them. And you have to submit before 22 of May. 22 of April. April is going on. 22 is April. You have to submit it before that. So there is no any question. So please wait a minute. I am going to take attendance. Scroll down. Okay, you can go now. Have a nice day and good night. Take care.
Recording stopped.